Throughout the course, we will have occasions to generate samples from various sorts of multivariate distributions. For now, let us conclude this topic on random variable generations by talking about how we can sample multivariate normal random variables. Let us use bold x to denote the vector from x1 all the way to xd. And suppose that x is multivariate normally distributed with mean vector mu, bold mu, which is a d-dimensional vector from mu1 to mu d. Covariance matrix sigma. So sigma here is a d by d matrix that is symmetric and positive semi-definite. And in this case, each of the xk's, so from x1 to xd, will be marginally normally distributed with mean of mu k and variance of sigma k. The covariance between two x's, xj and xk, where j is not equal to k, is defined as the expectation of the product of xj minus mu j with xk minus mu k. For sigma, our covariance matrix, the diagonal elements of this matrix will be the variances for each of the xk's. And the off-diagonal elements are the covariances, where the jkth entry is sigma jk, which is the covariance between xj and xk. Also, under the multivariate normal distribution with mean mu and covariance sigma, the joint PDF of x1 all the way up to xd is given by fx over here. The question we're interested in here is how we can obtain random samples from the multivariate normal distribution with mean mu and covariance sigma. Let's first consider a special case that is simple. This is the case where the mean is 0, so mu is the 0 vector, and sigma is the identity matrix, d by d identity matrix, which we denote by ID. In this case, we know that the sigma j case, which are the covariances between any two of the x's, is equal to 0 for any j not equal to k. For normal random variables, if they're uncorrelated, we know that they are independent. In other words, x1 all the way up to xd under this special case are independent and identically distributed according to the univariate standard normal distribution. Then we can apply a theoretical result, which is related to linear transformations of independent normal variables. And we can use this result to obtain draws for the general case where the mu is non-zero and the covariance is not the identity matrix, meaning that some of them can be correlated. So let's first take a look at this theorem. This theorem is related to linear transformations of independent normal random variables. Let's suppose that z is the d-dimensional vector from z1 to zd, and each of them is independent standard normal variables. In other words, we can also say that z follows the multivariate normal distribution with mean 0 and covariance of I. Further, suppose A is a d by d matrix and mu is a d-dimensional vector. Then, if we apply this kind of linear transformation to z by setting x equals a times z plus mu, then x can be shown to have multivariate normal distribution with mean mu and covariance a prime. You can also write it as x follows MVN with mean mu and covariance a prime like this. So this theorem allows us to transform independent normal draws to MVNs with non-zero covariance and non-zero mean. Specifically, If we want to draw d-dimensional samples X that follow multivariate normal distribution with mean mu and covariance sigma, what we can first do is to draw Z1 up to ZD from normal 0, 1, the univariate standard normal distribution. And then we let the both Z be the vector from Z1 to ZD. Next, we want to transform the Z's and they can become X. We compute X equals AZ plus mu. Mu, we know this should be the MVN mu. It's the mean vector of the multivariate normal distribution. And we want our A matrix, which is the linear transformation matrix we apply to Z, to satisfy this equation here, where A prime is equal to sigma. So how can we find such a matrix A? We can use Cholesky decomposition. So the textbook introduces several other methods, so 2 other methods that can be used to decompose the covariance matrix. And these 2 methods are known as the spectral decomposition and singular value decomposition. If you're interested in this, feel free to read section 3.6 on the textbook, which introduces the other methods. But for now, we will introduce the Cholesky decomposition, which is what I think the most straightforward method. So here's what the Cholesky decomposition does. It decomposes a symmetric positive semi-definite matrix sigma into the product of 2 parts. So this matrix sigma can be decomposed as the product of U transpose with U. Here, U is a D by D upper triangular matrix. So this Cholesky decomposition can be performed using the R-Chol function, which stands for Cholesky. It takes the original symmetric matrix, positive semi-definite matrix sigma as input, and it outputs U, the upper triangular matrix that satisfies this quality. So now let's see an example of drawing from multivariate normal distribution. Let's try to draw 1,000 samples from the 2-dimensional multivariate normal distribution with mean mu and covariance sigma. Here, mu is the 2-dimensional vector. Mu is 1 and 2, meaning that x1 should have mean of 1 and x2 should have mean of 2. And the covariance matrix sigma is given by this symmetric matrix over here. So we can see that by looking at the diagonals, we've seen the standard deviation of x1 is 1. The theoretical standard deviation of x2, sigma 2, is 0.5. That's the square root of 0.25. And then the correlation between these 2 random variables, x1 and x2, is given by the covariance divided by the product of the 2 standard deviations, and that's 0.8. So here's how we're going to apply and to get the draws. For each I between 1 and 1,000, we will first draw Z1 and Z2, each from normal distribution with mean 0 and standard deviation of 1. Then we will apply the Cholesky decomposition on the sigma, the covariance matrix, and try to obtain its decomposition and the transformation matrix that we can use. The last step is transforming the z's. We want to transform the z's by letting x equals A transpose times z plus u. And here's the code that implements this. The first line of code, we created a matrix where each entry is a standard normal random variable draw. There are a total of 1,000 rows and 2 columns. Each of the rows represent 1 sample, and each of the columns represent one of the x1 and x2, one of the 2 dimensions. Then we tell R what is going to be our mu and what is going to be our sigma. here, so because we want the final output to be the X matrix, which is going to be a 1000 by 2 matrix, where the rows represent the samples and the columns are X1 and X2, so the dimensions of the multivariate normal random variable. So what we do here for mu is to make a matrix where each row, there are a total of 1000 rows, and each of the rows is the vector of 1, 2. So essentially, it's 1, 2 on the first row, 1, 2 on the second row, all the way until the 1000th row. We want to be adding this matrix to A times Z later on. And our sigma, sig, the covariance matrix, is the 2 by 2 matrix where the entries are specified as follows. And the next step will be applying the Cholesky decomposition to the sigma. And let's call this matrix A. A is the output of the Cholesky decomposition of the covariance matrix, and it's going to still be 2 by 2, and it's lower triangular, the upper triangular. Sorry, there's a typo here. There you go. Okay, so now we have gotten the A matrix. We have the mu's and we have the z's. This means that we can perform the transformation of the standard normal independent draws into the multivariate normal x's. So here we perform a matrix multiplication where the x is going to be equal to z. You can see it's the 1000 by 2 matrix multiplied by A, the 2 by 2 matrix, plus mu, and mu is also a 1000 by 2 matrix. And the result is also going to be a 1000 by 2 matrix, where each of the rows we have performed the corresponding transformation. So each of the rows is one observation, and we have performed the appropriate transformation as specified in the earlier theorem. So let's take a look at our x's and see how some summary statistics look like. First, we want to confirm that the x's that we obtained using this way has a observed covariance matrix that is similar to what is implied by its theoretical distribution. Let's recall that the theoretical distribution, we know that the sigma, the theoretical covariance matrix, has some entries 1, 0.4, 0.4, and 0.25. And here, where we say round cov x 3, is where we look at the observed covariance matrix of our x samples rounded to 3 digits. And this is indeed quite close to our theoretical covariance matrix, which is nice. Let's further look at the means and see whether that agrees with mu. So we know that x is 1000 by 2, and each column represents one of the 2 dimensions. So we can do co-means to calculate what is the average, the sample average on each of the dimensions. And we can see that these are quite close to the theoretical means of 1 and 2 as well. In addition to looking at the means and the observed covariances, we can also try to create some pairwise scatter plots for the multivariate normal random variables. This can be done using the pairs function inside R. So by doing pairs x, it returns this pairwise scatter plot where, so these two should be the same. Each of them is the scatter plot of this pair of variables. So because we only have 2, so variable 1 and variable 2 over here, so we only have 1 pair. However, if you have more than 2 dimensions, you know that 1, 2 can have a pair, and 1, 3 can have one, and 2, 3 can have one. And from the scatter plot, it does look like they have a correlation that is quite close to 0.8. So that seems to agree with our theoretical multivariate normal distribution that we tried to sample from. So we try to implement this multivariate normal sampler using the transformation of the standard normals and using the Cholesky decomposition method. If you want to have a function that directly draws multivariate normal random variables for you, then you can use the RMVT norm package. After installing this package, you'll be able to use the functions inside for calculating multivariate normal density. So there's a DMV norm function for this. Calculating the cumulative distribution function, or the cumulative distribution, PMV norm, and to draw random samples from the multivariate normal distribution with certain mean and covariances. And this function is known as RMV norm.